All right, everyone, welcome to today's seminar. Thank you very much for making out the time. I know it's towards the final season. So today it's our pleasure to have Dr. Yurong, a senior research scientist. He just told me that he just got promoted, which is very good, at Nvidia Research. He joined Nvidia at the beginning of 2024, and prior to that, he was a PhD student in Cornell, for science. And prior to that, he got his bachelor's degree from Shanghai Jiaotong University. So he has been working in this domain of autonomous driving computer vision for doing his whole PhD career. He's working under Professor Marco Parbone, which was our original guest, and he cannot make it due to his busy travel. But it's great that we have Dr. Yu here because he's really at the front line of the research, and he can tell a lot about their research that they have been doing at their lab at Nvidia Research. It's all about autonomous driving. It's about all the frontier research that leverage all those the computing resources that they have at Nvidia. And one last thing before I hand over to Dr. Yo, the thing that he's going to talk about Alpamayo is actually something that's very popular in our domain. So I work on autonomous driving and also my students. Several of my students have been studying this Alpamayo for the past few months. So it's really fortunate for us to have one of the co-authors for that research to come here and present this wonderful research to us. So without further ado, let's welcome Dr. Yo. Thank you.
Yeah, thanks everyone, and thanks Professor Zhang for a kind introduction. And it's very excited to be here. To be Purdue is my first time. Been to Purdue University. It's a very vibrant campus and remind me of a lot of happy time when I was in Cornell. I'm currently a senior research scientist at Nvidia working on Alpamayo, and I'm one of the core developer for the Alpamayo model. So today in this talk, we will take a deep dive into Alpamayo 1, which is a reasoning-based VLM model. VLM is a VLA model. It's a vision language action model that is the key components of the Alpamayo ecosystem. Specifically, I will cover first how a reasoning-based VLA is designed and built, and second is that how we take the Alpamayo 1 to production ready and with some of our latest results. And finally, we will share some of our latest updates on the Alpamayo ecosystem. Okay. So now, as many of you may already know, at the latest CES and GTC, Nvidia unveiled the Alpamayo platform. It's a comprehensive open ecosystem of AI models, simulators, and datasets aimed at accelerating the development of reasoning-based autonomous vehicle. So the Alpamayo platform consists of three main parts. First one is the Alpamayo 1 model, as shown on the left. So this is the key focus of our talk today. So this model is an open weight, open sourced 10B parameter train-off stored reasoning VLA model built upon Cosmos Reason. Cosmos Reason is a vision language foundation model. It takes multi-camera videos as inputs and outputs both the trajectories as the future trajectory predictions that the car should make as an action, and also explicit reasoning traces behind each of the action it takes. And second one is the Alpasim. So it's an open source end-to-end autonomous vehicle simulation platform that is designed specifically for development and research. So what it does is that it enables closed loop simulation of the end-to-end AV policies. So what it does is that it simulates realistic sensor data, vehicle dynamics, and the traffic scenarios. And the last one is the physical AI dataset. This is one of the largest and most geographically diverse dataset we have that is available public. And it consists of multi-sensor and enables AI researchers to test their end-to-end policies on very diverse driving scenes. So everything in the Alpamayo ecosystem is opened. We have model weights, code, datasets, and tools available either on GitHub or on the Hugging Face. And Here, the link below is a Hugging Face blog post. It's a very useful entry point for you to navigate. It's a blog post written by Marco. It's an aggregate of all useful pointers of the Alpamayo ecosystem. So at the core of Alpamayo, we embraces the foundation models to accelerate every aspect of the development of autonomous vehicles. So to be more specific, by foundation model, what I mean is a model that is trained on very broad data, and ideally the internet scale data, and train it in a self-supervised fashion. And such model can be adapted to a wide variety of different physical AI tasks. And autonomous vehicle is one of the application. And Nvidia has been developing such model to support the development of physical AI applications. And we named it Cosmos. It's a Cosmos World Foundation Models. It mainly comprises of 4 main models. First is the Cosmos Predict, which generates the future videos or world states from a video or text prompts, very suitable for simulating scenarios of interest. And Cosmos Transfer, the second one, is that given some structural inputs, it can turn the structural input into some realistic scenes, which is very ideal for generating synthetic training data. And the third one is the Cosmos Embed, which is used to convert the raw video into a continuous latent token representation that can be readily used for data retrieval or the data curation for the physical AI training pipeline. And the last one is the Cosmos Reason, which adds a multimodal reasoning engine that interprets the video inputs and provides train of thought reasoning and the annotations. So the foundation models can be leveraged in every aspect of the development of autonomous vehicles. It starts by unifying and accelerating the offline development workflow, like I show on the left, from the data generation, data curation, sensor and traffic simulations, and the safety validations. It's accelerated the development, offline development of the models, and also it's also delivered substantial gains to the model we use on car by providing substantial generalizability and the safety guarantee. And the Alpamayo platform embodies such philosophy that using the foundation models from end to end. So for example, we leverage the Cosmos Reason as the base model of our Alpamayo 1 model. And we also use Cosmos Embed to curate our training data. And the future iterations of Alpamayo model will keep extending the use of Cosmos models in a wider variety of tasks. So conceptually, for what does it mean by foundation model empowered the development of the AV foundation, AV system, is that you can imagine we have a large, very powerful big brain running on the cloud to accelerate the off-board development. We also have a model that is small enough, fast enough, can be deployed on the car to to handle the real-time driving tasks. And I would like to emphasize that the AV development, particularly foundation model empowered AV development, is not a static or a sequential process. It's rather a cycle, really embodies the cycles of the AI data flywheel. So what it means is that we have a world foundation model to speed up the off-board development of the model. And once we get a better model, the better model will generate more realistic, more useful data that used to train the model. And the cycle, we have a AI flywheel cycle to keep this running. And then this is not only just one cycle, but multiple cycles from chip to the cloud, from training to the validation. And this is the full program impact of the foundation model-based development becomes even more pronounced as we are developing L4 autonomy, which requires substantial unprecedented levels of generalization, as well as the thorough validations of the model before it deployed. So let's get back to the Alpamayo 1 model. And before I introduce it, let me start by showing you a short video explaining the capability of Alpamayo 1 model, the core principles, and the tool associated to develop such model.
The next frontier of autonomous driving is enabled by the power to reason. This means developing models that can think through extremely rare or never-before-seen situations and act accordingly. Nvidia Alpamayo is helping make this happen today with an ecosystem of open components that brings together AI models with reasoning capabilities to make decisions, closed-loop simulation tools to test those decisions, and massive real-world driving datasets to learn from. Alpamayo 1, the first release in this family, is a large vision language action model that integrates visual perception, language understanding, and action generation with reasoning to explain its own decisions. Alpamayo 1 can more accurately perceive the environment, interpret context, and anticipate risks through reasoning. These explicit reasoning traces ensure logical consistency and trustworthy explainability.
So as shown in the video, Alpamayo 1 is an end-to-end reasoning-based VLA model developed specifically for AV applications. And unlike just normal VLA models, which maps maybe texture or video inputs directly into actions, what I mean by reasoning VLA is that it decomposes the task into manageable subtasks and articulate their reasoning trace step by step. So the Alpamayo 1 is designed to take as input designed to take as input images from multiple cameras across multiple times, and then to produce three main types of outputs: reasoning trace, meta actions, and trajectory as actions. And as we will see, such approach enables the model to perform tasks more accurately and also provides a degrees of introspection and can generate monitor signals that can be used for safety purposes. So what I mean here by reasoning trace is that I'm not claiming that this is such model can be capable of human level cognition. What I mean is that we design such reasoning process as a statistical process that can produce the reasoning trace that resembles how human will think in the same situation. So let me take this as an example. So here, this is the real clips we found in the data sets. So as you can see, if you are imagine you are a driver driving a car and encounter such situation, what you will do before you act. So first, you will need to think, oh, what happened? You need to understand what the scene, what the situation is. So here there are two cars stopped and several people are on the road and one person is chasing a cat. And then after you understand the scenarios, you will think, is there any risk? You will estimate the risk of such scenarios. So here it's actually a very risky scenarios where the person and the cat might suddenly run across into the lane I'm driving. And if I don't stop, I could hit them. And after you estimate it, you will take action. Is what you do next. So here we should slow down and stop until the road is clear. So why does this capability matters for high-end autonomy? Because if you just train a model from mapping the inputs, that is the image, to the actions, the model just does not know why it should take such action, and the supervision signal is very weak. So we structure the training data like this to specifically teach the model the link between the observations to the action it takes. And it turns out such supervision is very important to improve the performance of the model. And because the model also outputs the reasoning trace, so you can actually look into, for example, if the model makes a mistake, you can know, oh, why the model is making such decision by looking into the reasoning trace it produced before it produced the trajectories. Okay, So then after we talk about the key components of the models, the big question is how can we scaffold such embodied reasoning? How do we train such model? So to this purpose, we have designed a multi-stage training pipeline where several stages are used to enable the model to have both the capability to reason and the capability to produce accurate action. So we begin with Cosmos Reason, which is pre-trained on massive amount of data, specifically for the physical AI use case. And it has much better 3D understanding of the use case in the physical AI scenarios. And then from such Cosmos Reason based model, we have collected or curated a large amount of training data, specifically on the autonomous driving scenarios. So this step is to inject the action modalities into the model to make the model know how to take action, what the action looks like, how to interact with the world. And then after this, we have a specific SFT supervised fine-tuning stage to eliciting reasoning capability. So these steps, we have collected a data set that we have the auto-label annotations that teach the model why it should take such action at a specific time step. So after this, we also have a reinforcement post-training stages to further align the reasoning traces and the action the model produce. And the last step is that for onboard, you can optionally use a distillation technique to reduce the model to a smaller model that's still capable of running on the car, but still capable of generating accurate reasoning trace, but capable of running on the car. Okay. So in the remainder of the presentation, we will focus on 3 key aspects underpinning the design and development and the productionization of the Alpamayo 1. And first, I will provide more detail about our training strategy, highlighting how we generate or how we curate the reasoning trace for the Alpamayo model, and also how we do the RL post-training to align the reasoning traces and the action you produce. And second, I will discuss our latest research on how we represent different modalities in the Alpamayo model, including vision, language, and action. And third, we'll cover what it takes to productionize such model into a state that is production ready. Okay. So as mentioned, after we start from a model that has a general reasoning capability, and after injecting the action modalities, we use supervised fine-tuning with reasoning traits to elicit the reasoning. So this raises 2 key questions. First is that how can we generate high-quality reasoning labels at scale? Second is that how much does this reasoning training can help the model? So to generate the reasoning traces at scale, we need to carefully design the auto-labeling procedure. So this might think trivial if you did not pay too much attention on what's the cost it can be. You might think, oh, it's just you have a video, you have a trajectories, you just ask the VLM model to give an explanation of why you should take such trajectory. And we tried that in the first place, and it turns out it's very bad actually. It cannot generate the reasoning trace that is useful for the model. So there are 3 caveats we found if you just take such naive approach. The first one is the causal confusion. What does it mean by causal confusion is that the model refers to some aspects that is not visible to the ego car before the time we query. For example, in this video, the car is driving and taking a maneuver, and we ask at this time step why the car should take such actions. And the naive VLM models just outputs slow down to maintain a safe distance from the silver SUV, cutting into a lane from the left. But in the actual data, the silver SUV did not appear before this current frame we queried. So it's like you are teaching the model to use a future information to guide its current action, which doesn't make any sense. So this is one thing we found, that if you just naively use a VLM model to label. And to resolve this, we will have a technique will resolve this in later class. And the second issue is that sometimes the model will just have very vague behavior description. For example, in this case, the model, when we query the VLM model, what you should do next, it just say, please follow his instruction, but without explicitly say what you should do. It can be mapped. This can correspond to many different actions and make the model confused. And the last one is very superficial reasoning. So what does that mean is that the model does, the VLM labeling tool just does outputs a lot of reasoning traces, and a lot of them are actually correct. It's not incorrect, it's correct, but it's not useful for the model to make a decision. For example, it says what the driver of the eco vehicle should be careful is to avoid hitting any objects on the side of the road, which is applicable to any of the scenarios. It does not provide entropy. It does not reduce the entropy of the solving the autonomous driving in this specific scenario. So even though it's correct, but it's superficial, it does not help. And if you train the model to produce such long but not useful reasoning trace, it will not help the model. So to address these three limitations, we specifically developed a so-called chain of causation auto-labeling pipeline. And specifically, to address the causal confusion, what we do is that we anchor the reasoning generation to some key decision friends, referred as the key friends, such as when a traffic light turns green or when the car, there are some eco cars suddenly cut in. So this ensures the reasoning process only incorporates factors that occur before these key friends. And next, to eliminate the vague behavior descriptions, we have explicitly defined a closed set of driving decisions. We categorize the driving decisions into longitudinal and lateral with unambiguous types of vocabulary for each of them. So when we ask the model to auto-label the decisions, it only uses the vocabulary we provided. So actually it outputs, the labels it outputs will not be vague. And finally, we structure the reasoning trace in a causation format. So what I mean is that the final reasoning trace will look like this. It will list out the course it observed and link the course to the decision it makes. For example, here is to abort nudge to avoid collision with the incoming vehicle in the left, adjust the lane and stop for the vehicle in front, park on the right. So it explicitly mentioned why it should take and what it should take, why it should take such action and why it should take such action. So this discourages superficial reasoning. And remarkably, we found that after switching from naively using the VLM, that is an unstructured COT, to such structured chain of causation COT, improves the auto-labeling accuracy by 121%. So with this high quality data in hand, we use such data to train our model to self-supervise to do the supervised fine-tuning of the VLA model and transform it into a reasoning VLA. So on the left, we show that the model's performance across nominal cases, that is, you would say it is simple cases like land keeping or nothing really hard, nothing really weird happens in the scenarios. As you can see that with the meta actions and the trend of causation training, the model actually can do much better with the such training. And we also hand selected 500 challenging cases. These cases includes some very hard maneuvers or some long tail cases. These are very, you can, from the, we evaluated by mean AD, you can understand it as the model predicts the trajectory and the distance between the trajectory and the ground truth trajectory. So this, the lower the number is, the better the model performs. That's closer to the ground truth. So for this challenging scenario cases, you can see the mean AD is much higher than the nominal one. So this task is definitely definitely harder than these nominal scenarios. And we found that the gain from training with such reasoning traits is not pronounced on such challenging cases. So this demonstrates the reasoning has great impact on the complex edge case scenarios as expected. So far we have focused on eliciting reasoning, that is teaching the model to produce text-based reasoning traits that resembles the human thought. And let's say we must ensure the reasoning and the action generation are reflective of each other. They should be correspond to each other. And on one hand, to make the reason we need to do this is that first, we need to make sure the action generation can fully harness the reasoning traits it produce that follow the guidance of the reasoning traits. And second is that because we use the reasoning traits to do the monitoring, so we need to make sure the monitoring signal is accurate. So this is the scope of the post-training. So what we found is that after the supervised fine-tuning stage, the model can still produce trajectories that is not quite aligned with the reasoning traits it produced. What I mean is that, for example, the reasoning traits can be ask the model to stop and then wait for other vehicles, but the trajectory it produced is not doing such maneuver. And the reason that this happened is that first, the supervised fine-tuning data is limited compared to the original trajectory data. So most of the model length is to map the visual inputs to the trajectory rather than relying on the reasoning traits it produced to output a trajectory. We did not explicitly require the model to output the aligned trajectory with the reasoning traits. So we call this issue the divergence between the reasoning and the action generation embodied misalignment. So to address this, we use reinforcement learning to resolve this issue. So what we do is that we have designed a variable, design a number of losses or rewards, including verifiable rewards like physical safety, traffic rules. And we also use a larger model, teacher model, as a feedback to evaluate whether this reasoning aligns with the trajectories. And we also have incorporated human feedbacks into this IR reward. So based on this reward, we first train a large reward model to evaluate whether this trajectory generation and the reasoning generation is aligned and makes sense. And we use such model to do the final IR fine-tuning stage, IR training stage, to make sure the trajectory and the reasoning is aligned. So after the post-training alignment, we observed consistent improvement across both the motion generation faithfulness and the driving performance. So on the reasoning action alignment side, as you can see on the left, for example, the model reasons decelerate stops and then accelerate to a stop sign. Without the IR post-training, the model won't follow this reasoning trace very faithfully. But after IR training, the model can follow such an instruction. And on the driving performance alignment side, we also see very clear gain on using IR post-training. So we reduce the collision rate and also have better ADE. The lower ADE means a smaller error the model makes. So overall, this result showed that the embodied post-training alignment is not only the strengthen the fidelity of the reasoning, but leads to safer and more trustworthy driving behavior. So when we do the training of Alpamayo 1, we always have a curious question: how does this model scale with the size of the model and the size of the data set? And we found that the model can scale very well. So what we do is we have two ablation experiments. The first one is shown on the left. That is, we use the same amount of data, but train with different sized model. And as you can see, the larger the size, the model can actually have better results. So the same on the y-axis is the mean ADE that evaluates the error the model makes compared with the ground truth. The lower the better. So as you can see, bigger model will have better performance. On the right, we made a experiment by varying number of the training data we use. So as you can see, we vary from 3% of the clips, 7% of the clips, 17% of the clips to 100% of the clips. And we keep training the model with the same size of the model. So you can see a very clear scaling law that we marked the lowest mean AD on the bell set of each of the training run. And it scaled almost linearly with the data set amount. Okay, so after we talk about how we scaffold the reasoning trend of causation with the trend of causation and how we do the RL post-training, I would like to cover some of our recent research on how we can have the efficient representation of different modalities for the VLM models, including vision, language, and action. So the first I want to talk about is the action representation we use in the Alpamayo 1 model. So to enable the Alpamayo model to interact with the real world, we first need to inject the action modalities into the VLM model. The action modality, what I mean here is just the future trajectory of the ego car into our model. So due to the nature of the transformer models, we can naturally have two choices. First is we can encode the actions as discrete tokens. So by discrete tokens, what I mean is that you can just tokenize the waypoints. Here, for example, the waypoints is 12.3, 3 and 3.2, and next waypoints is 15.6 and 4.1. You can directly transform them into some discrete bins as discrete tokens. And this is basically the same as training the language model. Essentially, is teaching the model to speak a language that represents the future trajectory. So an advantage of this approach is that it's very easy to be integrated into the VLM training pipeline because we only need to train the model with the next token prediction loss. But the downside is that because we do such quantization, but the action is actually continuous. So you naturally have the quantization error when you represent the action like this. And to represent 6.4 seconds of the waypoints into the future, it takes a lot of tokens to represent such action. And if you ask the model to roll out, to do the autoregressive rollout of this many tokens, it will take a lot of time during inference. And on the contrast, we have another choice is represent the action as continuous representation. And we model the action by flow matching. So the advantage of the diffusion model or the flow matching model is that this can model the multimodal nature of the action very well as the autoregressive as found in our experiments. And there's no quantization error on the continuous actions. There's much smaller quantization error in the continuous actions. And also the inference time is controlled by the number of steps you use to do the diffusion, rather than controlled by the amount, the length of the tokens you use in a AR model. And also the diffusion model you use can be much smaller than the VLM, so your rollout will be faster. But because this is we represent the actions as continuous tokens, we need some special handling of such representation during training because it's not native to the VLM model. So in the Alpamayo 1, we are using an action expert model design, very similar to Pi 0.5, which is a mixture of transformer design. So what it does is that it consists of two parts. First part is the VLM, shown on the left. So this is a vanilla vision language backbone from Cosmos Reason. So we train this model by using the discrete tokens, as I described before, because you don't need to, you just train the model with the next token prediction loss without any other tricks. So it trains very well to that. This is to make sure the base VLM model understand the action modalities. And addition to the VLM backbone, we also have a action expert model that share the same architecture as the base VLM model, but with smaller hidden dimension to reduce its size. And what it does is that it will takes the KV cache from the VLM model and then do the diffusion rollout. And we also use the diffusion loss to train this model. So during inference, what it happens is that first we will have the vision inputs, videos from multiple cameras feed into the VLM, and also the user commands and the navigation as textual inputs to the VLM. And the VLM generates do the autoregressive rollout to generate the COT reasoning and the meta actions. And after it generates meta actions, we stop it. We stop here. We don't allow it to generate the discrete tokens because it takes a lot of time. And we use the KV cache in this stage and then feed into the action expert models to do the diffusion rollout. So with this design, we get a benefit of both representation. The VLM is very easy to train, and the diffusion can have a much faster rollout time during inference and much accurate action representation. So here I show on the left, I show what the diffusion looks like during inference. So here for visualization purposes, I use 100 steps. In practice, you can just use 5 or 10 or even smaller number of steps. So it's very fast. So you can see that the model can generate very accurate trajectories. And on the right, I show some evaluations on the trajectory prediction, either on the closed loop, safety, comfort, and also the overall inference speed compared with the autoregressive model. So we evaluated the model also both on closed loop and the open loop, and we found that consistently diffusion model perform much better than the autoregressive model. So after talking about the action representation, I would like to spend some time to talk about how we speed up the representation of the vision. So the current design of the VLM is usually you split the images into multiple patches, and then you use some model to encode each of the patch to some representation. So as you can imagine, if you have many images and many time steps, the number of the embedding tokens fed into the VLM prefilling will be linear to the number of image you fit in. So this limits how we can use more images to train the model. So one of the research we conduct is that we think the other way. How about we first encode the images into a latent representation and then fed into the VLM. So this is we call it triplane representation for the VLM policy. What it does is very simple. It's actually when you have multiple images from different cameras, you first transform that into a triplane representation that you can view that as a reconstruction of the 3D, but represent in a very efficient triplane representation. And the good thing about triplane representation is that it does not care how many images or how high the resolution is the image you fit in. It always outputs the same amount of tokens after the tokenization. So by doing this, we can use much higher resolution images and more images to encode the current scene. And we found that you can actually achieve better trajectory performance with less tokens. And another approach we explore is that we can, instead of relying on the structural bias we put in the triplane, we can actually fully use the data-driven recipes for encoding the images. So what is word we call it flex. What it does is that you have multiple images, and we use some flex scene encoder that transform this multiple images into some fixed amount of representations, fully trained self-supervisedly, and use such compress representations fit into the VLM policies. And we found that you can actually do much better than the baseline. Yeah, I will not expand here, but feel free to check it out. We have the link below. Okay, and in terms of the reasoning, the modality of reasoning, so what we have covered is purely textual reasoning. That is, we represent reasoning as English, plain English, either by the train of thought or by train of causation. And we can, but the reasoning is not necessarily limited to such representation. We can have counterfactual reasoning like human. We can have reflective thinking. So we can first propose an action and think, oh, I should not actually have done such action. We should do it the other way. We call it counterfactual reasoning. And we also can reason not only on the plain English, but on multimodal data, like images, or like the latent reasoning I will introduce later. So let me give you one example of our recent research. We call it counterfactual reasoning. So what it does is that, as you can see, there's an example on the right. A pedestrian might potentially cross in front of the vehicle, and the system initially generates a meta-action plans. The meta-action is high-level plans of the trajectories, and it generates a plan that is keep speed and accelerate. And if the model executes such plans blindly, the car can hit this pedestrian very easily. And the model then reflect on this action it proposed and think, oh, wait, I should not have done such action because I might have hit the pedestrians. And then it proposed another corrected meta actions. So this is what the final model looks like of this paper. And the way we do it is very interesting. We use a fully data-driven way to train such model. We did not manually design any way to ask the model to do such counterfactual reasoning. And also the model produced the counterfactual reasoning adaptively. So on the left, you can see the rate of triggering such counterfactual reasoning will change according to the difficulty of the task. So by difficulty, what I mean is that the trajectory errors of the task. As you can see, if the error is higher, the rate of the model initializing such counterfactual reasoning is higher. And also you can see with harder tasks, after model performs such counterfactual reasoning, it can have better results. And regarding the reasoning modalities, well, English text is very easy and a very common way to represent reasoning is what we use in Alpamayo 1 model, and it's not necessarily the most efficient way of thinking, because as a human, some thinking, it's very hard to argue you're thinking English or you think in a latent space. So in this work, what we explore is that instead of thinking in plain English, we think it in the latent space that represents the world, the scenarios around the ego car. And by thinking, what it means is to roll out what it looks like in the future by rolling out such latent representation. And we also show such thinking can be much faster than plain English thinking, and it can improve the output trajectory quality, and it's very suitable for RL training. Okay, so this all looks very promising. And lastly, I will briefly talk about how we, Nvidia production team takes the Alpamayo research into production ready. So this is one of the evaluation we did on the AlpaSim. So we evaluate our models on the closed loop simulation across a variety of challenging tasks like urban scenarios results, confirming the performance of the improvement discussed before. And the simulator we use is the AlpaSim, is part of the Alpamayo ecosystem. It can be freely used. You can download it online and try it out. And build on these results, we the production team in Nvidia is working on making it really run on the car. So let me show you a short video, quickly demonstrate how it looks like on the car. Audio is not correct. Let me change it. It's like coming from the projector.
Sure, turning right ahead.
Hey, Nvidia, what are you doing?
I am stopping at the stop sign at the intersection.
Okay, so it's very interesting here. The model not only is driving, but also explaining what it's doing, and also takes the interaction from the user to change its driving behavior. So this gives a glimpse of what we envisioned the L4 level driving should look like. So what it means is that the vehicle is not only autonomous, but it can interact with the humans that is sitting in the car. So I will provide a brief introduction of how we make this into production. So there are many challenges to make such a large foundation model running on a car, as you can imagine. The first of the challenges is that you need to run this in real time. Because the car is driving on the road, you need to have the real time responses. By real time, what I mean is about 10 hertz. So running on, like reducing the inference latency of this large foundation model is very difficult. And second is that we need to have such labeling of such data that capture how the user should interact with the model. But the data we recorded does not have such labels. So we need to make up such labels. And third one is that we need to have production grade data curation, because what we found is that the trajectory it produced is strongly linked to the reasoning trace it produced. So in order to make sure this alignment, we need to have very good high quality data to make sure they align. So I will briefly talk about the last two here. So in order to have a production grade data curation, we have done two things to make sure both the data is diverse and is of high quality. So in order to have a very diverse data, what we do is that we will have recordings logged from the car, and then we will classify each of the clips into different scenarios and have a structure, like tree structure, that classify into different categories. And we will iterate on the model performance, either in simulations on the car, to update how we like each fraction of these scenarios in the final training data set. And during past year, as far as I know, production team has iterated this over 100 times to have a stable recipes of the data. And on the right, we leverage the auto labeling pipeline, as I described previously from the research team in the production that use this auto labeling as a VLM auto labeling to label the keyframes and the reasoning trace for the clips. And we also conduct several very comprehensive filtering of this data, and also have the human evaluation of the data to make sure the reasoning trace is accurate and is useful for the model. And in order to make the model online and have very low latency, production team actually have a lot of optimizations on the model design. First one is that we use speculated decoding to reduce the time it takes to generate the reasoning tokens. And instead of using vanilla, for example, cyclipped image encoder, we use a radial pre-trained fast efficient VIT encoder that is very efficient to encode images into continuous representations. And in order to use such pre-trained fast efficient VIT, we employed a multi-stage training techniques that make the pre-trained VRM to adapt to the new vision representation. So all these three and many more, we made a Alpamayo model on the car. Of course, it's not a 10B model, but a distilled version of the model. So, so far I have illustrated our journey from the research to the production in delivering a reasoning-based VRM, VR8 for onboard AV autonomy. And in the final part of this talk today, I will share some of our latest updates on the Alpamayo ecosystem. So first, in last GTC, we announced Alpamayo 1.5. It is still a 10B parameter model, but now it supports navigation and text prompt for guidance, making it more easily to steal. What it means is that you can take texture inputs like navigations from the Google Maps, like turning right in 10 meters. You fed it into the prefiltering stage of the VLM, and it can take the changes. It will take the turn. And we also support flexible camera configurations. You can either use just one camera or 4 cameras to do the inference. And additionally, as requested by many developers, we have released the post-training scripts both on SFT and IL fine-tuning, IL post-training, to help the developer to fully customize the Alpamayo 1.5 or Alpamayo 1 models to their use case. And on the simulation side, we have expanded a set of neural artifacts on the AlpaSim to enable end-to-end testing of the policy in a large amount of realistic scenes. And on the data side, we have released, actually here is we have already released some of the reasoning scenarios. Yeah, I think we have released some of the reasoning, like challenging scenarios, specifically selected from the physical AI dataset, but the reasoning labels and the COC auto labeling pipeline is still in the internal process. We'll release them soon. And we are planning to launch a reasoning benchmark focusing on this challenging scenarios. So more information can be found on the link post below. It's a very good entry point that aggregates all the useful informations about Alpamayo. Okay, I think thanks for your attention. This is the end of my talk today. Hope you enjoyed.
Very structured talk. So now we can open the floor to questions.
And I have 2 questions. So the first one, I'm skeptical to trust the reasoning chain of large language model, especially when I use it for my work. So sometimes it gives me very good reasoning, but wrong results. And sometimes my result it gives me a correct result, but the wrong intermediate steps. So my understanding, the large language they will not generated by another large language model. So is it possible that a reasoning chain some intermediate step is not consistent or wrong with the other the reasoning steps, and that will degrade the performance of the model?
Yeah, definitely. Very good question. And we also found this issue when we developed the Alpamayo 1 model internally. And what we found is that first, the auto labeling quality is very important. If you just simply use the VRM generated auto labeling, it won't work. You need to use the channel of causation, like structured COC reasoning. Such label can enable good reasoning from the model. And second is that even with this, the models can sometimes output the wrong reasoning traces or the wrong trajectories. And we found that we need to use post-training like RL to explicitly align both modalities. But this is still not perfect, and we are still actively doing research on this.
I also have So, I think a major limitation for current open modeling is that it's very difficult to handle the long tail events. So how are you handling this? Are you doing data augmentation into your data set, or you're manually labeling some kind of events?
Yeah, also a very good question, and thanks for asking this. I think the reason we want to use foundation models for autonomous driving is to solve the long tail cases. So different from traditional like end-to-end models by all the data-centric way of solving this. What they do is that they will collect a large amount of driving data and train a model on this driving data. But you cannot cover all the cases in such driving data. So our approach is different. Instead, we want the model, we start from a model, we start from a model that is capable of common sense reasoning, that is trained on very broad internet scale data set. And such model can generalize much better than the model you collected on a car, because the data you collected on a car the diversity is much less than the data the model sees on the internet. So we start from a foundation model that is pre-trained on the internet, that we assume it to have in the future also have much better general understanding capability, general reasoning capability that can solve such long tail cases. So we start from that standpoint, and we adapt it to the autonomous driving cases. So by doing this, we think this is the way to solve the long tail cases in a systematic way.
You fine-tune the model with a certain challenging or long tail events?
I think we do both. We have labeling on the nominal cases. We have labeling on the challenging cases. We train on both.
You have some special mechanism to prevent this from forgetting, because the previous model is the internet size.
Yes, that's also a very good question. I think we are mixing some of the BQA data sets to make sure the model still keeps the original reasoning capability or language ability. Yeah.
There was a question from Anna.
Yeah, so it seems like there's a lot of, explainability, but there's a counterfactual reasoning in the chain of causation. But has, I guess, like your lab will thought about like using mechanistic interpretability techniques on the Alpamayo model, so like example training a sparse out of your certain tracing to actually determine if the reasoning is aligned with the output?
Sorry, I did not hear quite clearly. Could you
Sure.
speak larger?
Yeah, so basically, right now you're doing a lot of explainability with the reasoning traces, kind of actual reasoning in the data set. But has your group considered or experimented with mechanistic interpretability, so sparse autoencoders or other techniques to actually determine if the neural network itself is aligned with the prompt, or is it just pretending to be aligned with the prompt? That makes sense.
I see. Yeah, we did not actually do such exploration, but I think it's very interesting. It's like to do an introspect into what a model is actually learning. And we have some initial experiments, for example, looking into the attention maps of the models, that confirming the model is still indeed paying attention to the correct position. But we didn't do explicit, as you said, speculated a sparse autoencoding to make sure it has like compressed or explainable features inside the model. I think that is still a very interesting research direction, but we didn't focus on this in the Alpamayo development. Thank you.
Thank you for the great talk. You kind of touched on the role of the simulator and also using the omniverse for synthetic data. Could you maybe elaborate on how the synthetic data comes into play, and also how if it's using if any parts of the simulator is used for training or testing, how does the sensorial gap addressed in deploying on real world environments such that it actually performs in the same way that it is done in this?
I see. Yeah, very good question. And the Alpamayo 1 model we release actually does not train on this synthetic data generated, but we do test it on some of the synthetic data, like you have some use Cosmos Predict to transform a structured inputs into a realistic scenarios, and we test the model on this to verify the model can do some expected maneuver in some scenarios we want to test. I think in the future, first, I will envision the simulated data can be first very useful in the evaluation, and then we will use it more on the closed loop training to really teach the model to how to do the correct maneuvers in some of the cases.
Just go ahead and then we'll see. Go ahead.
Thank you. Most of the process that you see up there was very optical based, it was just a video. I was curious if there's any effort or insights or interest in incorporating, say, LiDAR radar measurements or even audio use with the words into the process. If that would just be, main things at the optical more optical.
Yeah, thanks for the question. So as far as I know, for the L4 program, we do plan to use LiDAR. But as you say, it will add the complexities to the system because the VLI model, they are pre-trained on the internet scale data on only text and images. It does not understand the LiDAR modalities. So you need another adaptation stage to make sure the model understands the LiDAR modalities. But I think in general, the recipe should still apply on like on the applications where you need the LiDAR. Yeah, but currently the model we release does not have LiDAR, but it may really contain LiDAR in the future.
And
Thanks.
we'll take two last questions right there, then if you have this.
So I have a question about the latent space on reasoning. So firstly, like, how do you determine which variables you want to encode in the latent space? And let's say you have like 10 candidate latent variables. How do you determine before training which of these variables, if encoded, would significantly like improve model performance most?
You mean the latent reasoning?
Yes.
That paper? I see. I think we are not determining this by handcraft latent space. It's all like all data driven. It's like determined by the model. Yeah, as you encode the future states into some latent representations and you roll out in latent representation. Yeah, you can check out the paper in detail. Thanks.
So it seems like the channel position is kind of recently developed and choosing such right decision for challenging scenarios. But how does it perform in terms of latency? Because then again, real world driving scenarios, latency is another different problem. Also, how do you compute these models like in the real world? Is it computed on the edge or is it computed on the cloud? Or if it's computed on the edge, what kind of process do you use to use? And is there a kind of bottlenecks to this process?
Yes, that's very good question. So when you try to deploy these models on the car, so the first question is that we use the model when you deploy on a car, we always run on car. We don't run it on cloud because there are some network issue can really be disaster to the model. And when you run on a car, latency is a big issue. And it turns out that you can have a lot of ways to reduce the latency. For example, the speculative decoding of the decoding the reasoning tokens. And also there are some recent works from Zhijian. He's a good friend of mine. He currently is a professor in UCSC. They have some very interesting techniques, combines both diffusion and the autoregressive to reduce the decoding time quite a lot. So if you do it naively on a car, it won't work. So it will take definitely much longer. But there are some very clever ways to do this to reduce the decoding time.
So like what's that kind of typical rough number of decision model space? So also, I guess there are also some model compression. You mentioned it also.
Yes.
I don't know. You use the. Model compression.
Yeah, because it touches the production, but I'm not sure how much I can disclose here. But it's using a model smaller than the model we released publicly. In terms of the latency is within 10 hertz. Is faster than 10 hertz. So that means the model we deploy on the car is running faster than 100 milliseconds to produce one prediction.
All right, so Dr. Yo will be sticking around for like another 30 minutes or so. So if you have any other questions, feel free to come and talk to him offline. But let's thank the speaker one more time. We will have our one last seminar next Friday. The guest is from Google DeepMind, so it's going to be also very exciting talk. So and good luck to your final. Thank you.
Those are